Good afternoon. So last time we started with pipelining, the concept of pipelining to increase the throughput of a circuit. And today we are going to look at how to pipeline the processor you had designed in Lab 6. I think it's on. Huh? Oh, I see. Can you hear it now? Okay. So again, it went off, is it? Can you hear me? All right. Let me just plug this into. Now, just to start out with, let me tell you that if you find this topic difficult, uh, you shouldn't be surprised. I mean, pipelining processors is one of the toughest uh, topics in computer architecture, and there is no end to the sophistication. So we are going to learn very basic concepts today, and for your project, you'll be designing things which will go much faster than your multi-cycle processor. Why is processor pipelining so difficult? First of all, we have very stringent correctness requirement. I mean, you can't come back and say, well, some instructions it does all right, right? I mean, if you have an ISA, all programs have to execute correctly or according to the semantics of the ISA. The second thing is, and this is absolutely new because we have no analog of it in ordinary pipelining that we will see. So we understand pipelines, we understand feedback, but there is something brand new that happens in processor pipelines, and that is the concept of speculation. And you will discover that unless we speculate, we can't pipeline at all, the processors. And the moment you hear the word speculation, it's guaranteed that there is going to be rollbacks and squashing and so on. What if your speculation was wrong? So we have to understand all these concepts. What does it mean to speculate? How do we speculate? How do we detect that the speculation has gone wrong? And then how do we roll back to the proper state? Uh, and as you will discover very quickly, processor pipelines have feedback in several places. And whenever there is feedback, you insert one extra FIFO, one extra register somewhere, it can change the semantics. So that becomes a correctness argument. Are you still preserving the semantics of ISA as defined by the multi-cycle implementation you did? And overall goal of ours remains that given a power requirement, given an area budget, what is the fastest processor I can build? In the old days, we used to say, well, build me the fastest machine you can. That's no longer the case because if I'm going to build a processor for smartphone, it should not dissipate more than 5 watts. I mean, the total device should not dissipate more than 5 watts. Otherwise, you won't be able to hold the phone in your hand, which means the processor in it really dissipates much, much less than even a watt. So then the question becomes, what is the best architecture you can come up with? What is the best strategy you can come up with for designing a high-end processor for your smartphone? And you will see this kind of restrictions everywhere we design processors. All right, so let's begin with the Lab 6 processor, which was a multi-cycle uh, processor. And you have seen this diagram a gazillion times. The main point in this is that suppose you have what happened to the non-load instruction. So you will do a fetch instruction fetch and goes to the memory, then you will get the instruction, and then we do everything in the second cycle. We go and decode it, we go and execute it, update the register file. That's the end of the story, right, for non-load instructions. But if you have a load instruction, then you will have to do a fetch, you will do an execute, then you issue a load request to the memory, and you have to wait for the answer to come back. So there is a third cycle that is involved, right? When the answer comes back from the memory, then you will go and write it back into the register file. So looking at things like this, you can do very simple-minded analysis. Let's suppose in my dynamic instruction mix, when I execute a program, 20% of the instructions are loads. Not very unrealistic, right? So 20% of the instructions are loads. Then what you will discover is that 80% of the instructions execute in 2 cycles, while 20% of the instructions execute in 3 cycles. So the total number of cycles you will take to execute that code will be on an average 2.2 cycles per instruction. Okay? So some instructions take 2, some instructions take 3, and you can do the mix. And that depends on the program, of course, that you are running. But it will not be 2, right? Because there are always some load instructions in your program. So higher memory latency. I mean, I assumed in this analysis that you went to the memory and you got the result back in the next cycle. But you know that if you have a cached memory system, once in a while you're going to get the result much later, much later, because you got a cache miss. And that's just going to make this equation much worse. You can add these numbers if you want. You say, let's assume there is, 1% of my cache requests are misses, and suppose they take, put some number in, 100 cycles or 10 cycles, and you will see this number goes up from 2.2 to much larger number. So whenever you have to deal with memory latency, throughput can decrease if the memory latency is large. Other thing to observe about this circuit is, by drawing these big blobs, what I was trying to show you is when we are doing fetch, the rest of the machine is doing nothing at that point. All that hardware is just sitting there. Similarly, when we are doing the execute part, fetch is doing nothing, etc. So at any given moment, there is a lot of unused hardware. So wouldn't it be wonderful, while I'm executing instruction I go and put the next instruction, I start fetching instruction I plus 1. And the moment we do that, then we are talking of pipelining. And today's lecture is about that, to understand what happens when we do that. All right. So what are the new problems that arise in pipelining? And the first one is the one that surprises everyone. So I have given you a pipeline where I've just drawn, it's a two-stage pipeline. You do a fetch and then rest, whatever. Sometimes it takes 1 cycle, sometimes it takes 2 cycles, this right-hand side of it. But notice what will happen. Suppose this side is executing, the execute side is executing instruction I. When do I know what is the next instruction to be fetched? When do I know the PC of the next instruction? You at least have to decode it, right? Right? You have to decode it to say, oh, it's not a jump instruction, etc. Therefore, this is the next instruction must be PC plus 4. Otherwise, you have to wait until you decode. So now you have a problem. And if it was a branch instruction, then you will have to wait all the time and until it finishes execution, and only then you will go and fetch the next instruction, because that's the only time when you know the real PC for it. So basically, control hazards are about the fact that I don't even know what the next item in my pipeline ought to be. And the common solution to this problem is speculate.
The solution is speculate. Just guess what is the next instruction. So if you are executing instruction at 100, then you just guess that the next instruction will be 104. And if you believe that the jumps are no more than 25%, then at least 75% of the time you're going to be right. Right? It is going to be PC plus 4. But since it was a guess, sooner or later you have to figure out whether your speculation was correct or not. And if your speculation was wrong, then you'll say, oops, and you'll have to go and kill the instruction that had been fetched, etc. So we have to do some work. So that's the basic idea of control hazards, anytime you have control hazards, only way we can make progress is by speculation. The other concept is data hazards, a new problem. What is that new problem? So suppose, I have a 3-stage pipeline. So now I'm saying, decode and execute, let me separate them. So decode decodes the instruction, goes and reads the registers, and then it passes it on to the execute. And what we want to do is we want to keep these three stages going in parallel. We want an instruction in the fetch stage, we want an instruction in the decode stage, and we want an instruction in the execute stage. So what is the new problem we face? The ISA semantic says that if I execute instruction at 100 and the next instruction is at 104, it must see all the effects of the previous instruction. It must see the register file values or PC value or memory values left by the previous instruction. That's how we describe the instruction set, and that's how your multi-cycle processor works. It finishes the execution of one instruction, and by that time all the states of the processors have been updated properly, and then you go and start executing the next one. But here we are being very eager. There is an instruction I-1 in the execute stage, and suppose it's going to update register R1, and it just so happens that the instruction in the decode stage wants to read R1. First of all, will it be able to read R1? Absolutely. Hardware doesn't stop it. Go and read the register file anytime you want. It just so happens that the register file contains stale values at that point. It hasn't been updated yet. So whenever you have a data, these things are known as data hazards, data races, that you read it too fast, right? You have to wait, until the right value is available. So the solution in this case is, if you think there is a possibility of reading stale values, then you just stop the instruction. And whatever is in the pipeline keeps executing. Sooner or later, any instruction that is ahead of you will complete. It will leave the system. And by the time it commits, that means you have updated the processor state. And now you will discover that this instruction, which had stalled because of data hazards, it can also move. So you are seeing two very, very high-level solutions to the problems we face in instruction pipelining. One problem, I have no clue what the next instruction ought to be, and we're going to speculate. And we speculate, then we have to squash when speculation goes wrong. Second problem, that I have to make sure that I'm not reading stale values. So I have to somehow detect, am I reading stale values? And if I'm reading stale values, then I have to stop. Right? So today's lecture is trying to understand all these ideas and what kind of solutions people have come up with, which are very, very general for solving these problems. Right? And another thing that remains true is, if you imagine a pipeline going like this, and I'm waiting for register R1, right? But I know that stage in the pipeline has the value of R1 because that's the instruction that was writing it. Well, maybe I can provide a new hardware path from that stage to the stage where it was waiting. And anytime you do that, these paths are known as bypasses, right? You're adding some extra data path to move the data faster. It's really literally like a shortcut. And how bypasses are used, how they are introduced, we study all that. And in your project, which is you're going to see very soon, it's all open-ended, so you can improve it, and you say, just another bypass, and I'll get the top of the hill by doing this in terms of performance, etc. Okay, so the plan is, I'm going to discuss both of these abstract pipelines. I showed you a 2-stage pipeline and a 3-stage pipeline, and by stages I mean when I can have 2 active instructions in the pipeline, or when I can have 3 active instructions in the pipeline. More than 1 active instruction in the pipeline means it's pipelined. In the system means it's pipeline. All right. And another wonderful thing is that most of the code you have written earlier will almost all be reusable, in doing the project. So you don't have to rewrite your ALU again unless you want to. You don't have to. You have to make very small modifications to the decoder, etc. Our whole emphasis will be how to make the pipeline work, right? So there is going to be extreme reuse of code that you have already seen. Okay, so let's analyze control hazard. How do we deal with this? So fetch stage initiates instruction fetches and sends them to the execute stage. So I like to think of these pipelines as flexible pipelines, or think of this FIFO as kind of a spring, so this guy keeps dumping instructions in it, and the other guy keeps pulling instructions from this queue, and both are going merrily, they're both executing. But we have already agreed that in order for it to keep fetching, it has to keep guessing, what is the next PC, etc. In this, now when executes an instructions, it may take one or more cycles to do so. We don't care, but instruction is executing and two things are active at the same time. The problem is the two stages can operate independently except for the case when the execute says, uh-oh, speculation failure. The instruction that is coming behind me is wrong because you told me it was 104, but actually this was a jump instruction and that instruction is going to be 208. So what to do in that case, right? What to do? So execute stage may want to go and correct the PC. It may say, no, whatever guess you had is wrong. And then all the instructions that have been fetched, by the time this detection is made, and all the instructions that have been fetched, when you set the correct PC, all these instructions have to be thrown away. They cannot be executed. They should not be allowed to modify the state. Okay, so let's try to understand this in terms of a timing diagram. So this was my multi-cycle processor, right? 2-stage, 3-stage, not 2-stage, I mean 2 cycles or 3 cycles it was going to take. So let's assume we have this instruction sequence here where I2 is a load instruction. So what will happen? I0 comes in. It's not a load instruction, so I can go and execute it. Then I go and execute I1 after that, and I execute I1, then I go and execute I2 after that, and it's going to take one extra cycle because it's a load instruction, so it goes here and it also goes here. Is everybody with me so far? I mean, this is your multi-cycle processor that you have already designed, and then you will go and fetch the next instruction after that. Now let's see what happens because of pipelining. And I'll give you a hint. Because of pipelining, the packing is going to get tighter. Many things will move back, right? Because we are doing them concurrently. Because when you look at it like this, in any time slot, only one entry is there. That's the only part of the pipeline that is doing anything. That is the only part of the system that is doing anything. Okay, so now let's take this and turn it into a 2-stage pipeline. So I can do a fetch and put it there, and once it's in the execute stage, it still takes 2 cycles, right, to execute. Sometimes it takes 1 cycle, sometimes it takes 2 cycles to execute. Let's try to draw a diagram for this. So in the fetch stage, I go and fetch I0, all right, and in the next stage, I0 will move to execute. And what else can I do? I can put I1 also here, right? So now I1 is being fetched at the same time when execute is executing I0 instruction at that time. And now the reason I have to look like this is my eyesight is not good enough with these glasses. I can see you, but I can't see my screen. All right. So remember, I1 is a prediction. The PC, the next PC to fetch, I haven't looked at I0 at all. And I'm saying, well, let's just assume it's going to be whatever PC it was, it's going to be, so this is my guess for it. Okay, and you'll do it, and you'll keep doing it like this, right? I2 was the load instruction in this case, and I3 comes in. Now what will happen? execute stage has only one place, right? And that is right now busy because it's waiting for a load. So there is a bubble, there is nothing that can be entered into the execute stage. It has capacity to hold only one instruction. All right, so that's why you will have a bubble, but after a while you will execute I3 here in the next cycle. I hope this is clear to everyone, when you will stop, because the data is just not available, right? And the capacity is limited. You have only one place to hold only one instruction over there. But what I want to point out to you is what happens if your speculation is wrong. So suppose I0 was a jump instruction or branch instruction of some sort, right? And after that, instead of executing I1, the instruction I really want to execute is I7. Okay, so let's do analysis of that case. So I have I0 comes in, and I1 is being fetched, and at the end of this execute cycle, I say, oops, wrong, your prediction is wrong. It's not I1, it should be I7. So what you will have to do is, it's I7 you have detected. As is the speculation correct? If its speculation was correct, it will be this. Otherwise, you have to cross it out. You have to throw it away. You have to make sure that under no circumstances I1 can modify the processor state, because this is a wrong path instruction. This is not an instruction that you were supposed to execute. Bad luck that your speculation was wrong in this case. And while you are doing that, so this is the squash, but at the same time, now you can start fetching I7, because now you know the correct PC at that point, and so on. So does everybody get the idea that at some stage we detect that my speculation is correct, then everything is hunky-dory, we keep moving. If we detect the speculation was wrong, then we have to look back and say, oops, stop, cancel this. This is the new value of PC, etc. That's the high-level idea. Okay, so the question is, how do I detect a misprediction? Any ideas? How will you detect it was a misprediction? What information do you need in order to know that the instruction that is coming behind you is wrong? Yep. I'm afraid you have to speak a bit louder.
We need to know the actual instruction that we
Right. So what we can do is, I can say, oh, my speculation, my next instruction is going to be this one, right? So current instruction is PC, and the prediction I'm making for the next instruction is, let's call it PPC, for predicted PC, and I pass both those pieces of information forward. At some stage in the execute, I know what should be the real next PC for the PC, for the instruction you were executing. And if it turns out to be your prediction PPC, everything is fine. If you detect that the instruction execution is telling you the next instruction is I7 and your prediction was I1, you say PPC is not equal to the next instruction, we'll call it a misprediction at that point. So what I'm saying is, you have to carry some information forward, and that information is your prediction, the prediction you had made. Carry it forward, and if there is a mismatch, whenever you detect it, you say, okay, things have gone wrong, let me fix things in the back. The instruction at PC carries the prediction with it as it flows through the pipeline, and at execute stage we know the real next PC. It is a misprediction if PC is not equal to PC. This is a simple idea, and I want everybody to remember it, because when I say misprediction, this is the image that should come to your mind. We know the prediction and we know the current PC, and say something has gone wrong, and whenever there's a misprediction, we'll take some actions. Okay, what does it mean to squash instruction? I used to say kill instruction, but I'm told that's not very politically correct, so we'll squash them. All right, so instruction should have no effect on the processor state. Really, that is the most important thing. If you're just reading a register, I don't care. If you're doing a load, I don't care. right? But on the other hand, if you're going to update the memory, if you're going to update the register file, if you're going to update the PC, absolutely not. So squashing an instruction means it should behave like a no-op as far as state updates are concerned. And there is no room for error in this. You can say, well, I almost got it right. No, I think if you updated even a single register which should not have been updated, it's just wrong. Okay, so we have to be very, very careful about that. And for stores, we can't see things directly. So store, my favorite analogy for stores is it's like launching a missile. And once you have sent the store to the storage system, to the memory system, you should assume it will be done sooner or later. And you can't say, sorry, I made a mistake, please send it back. Not allowed. So we'll be very careful. We never send any store into the memory system if there is a possibility that that store may be wrong. It may be uncalled for. All right. These conditions are easy to ensure because our system is, the one we are discussing, it's very simple. There is only one instruction in the execute stage, so it's not intellectually or mentally very hard to keep track of it. You know, what is this instruction going to do? And we'll take care of it. Good. Now, what I'm going to offer you here is a very, very general solution to the notion of how to take care of control hazards. And this solution is known as Epoch-based solution. And it's very simple, very, very simple. We are all going to understand it in the next 3 minutes. All right, so the idea here is add an Epoch register to your system. So you had until now PC, register file, and I'm saying, okay, one more register called Epoch. And what I will do is, any time I detect a misprediction, I'm going to change the epoch. Suppose we were executing, all the instructions were red, and we go there and we find, oops, mistake, speculation, failure, misprediction. I change epoch from red to green at this point, because that's a declaration of the fact now. Once the epoch has changed, anything that comes with red tag is wrong. You know, it's wrong path instruction at that point. Okay, so let's see what will happen. The execute stage changes the epoch whenever it detects a misprediction. All right? And the fetch stage associates the current epoch to every instruction sent to the execute stage. So whenever I send an instruction forward, oh, I forgot to explain, what is NAP? This is just a short form, right? Because this is the next address predictor. PC plus 4, right? In the simplest form. The reason I'm using the word NAP is, believe me when I tell you that there is so much research that has gone on to predict what should be the next instruction. Hundreds and hundreds of papers, right? And you will at least study one scheme, and if you use that scheme in your projects, you will get far better results. But I'm jumping ahead in my story. So NAP just stands for next address predictor. In the simplest form, it's simply PC plus 4. Okay, so please notice what is happening here. What am I putting in this F to D? Of course, I have to pass the PC forward. I'm passing my prediction forward, PPC, because which is the output of next address predictor, because I need these two pieces of information to detect if there is a failure, right? If there is a misspeculation. And I'm also passing the current epoch. So if we start out with red epoch, then all the instructions are going to be colored red, you know, from that. And I will carry all this information forward. In the execute stage, misprediction. What will happen? Red will be marked as green at that point. So now every instruction that goes to execute from then on will have a green tint to it. And if you saw any instructions with red, that means it should be thrown away. You know, this is coming from the wrong path instruction. Epoch of the instruction is examined. When it is ready to execute, if the processor epoch has changed, the instruction is thrown away. Do you get the idea of epochs? there's an epoch register, I taint everything with it in the fetch stage, right? It keeps going forward, forward. And by the time I get to execute, if I discover epoch has changed, that means, well, I was on the wrong path. This instruction, something happened behind my back, which is really forward, because these instructions were ahead of me. And I was just a speculated instruction. So if the reality has changed and they're saying this speculation is wrong, then it has to be thrown away. A very simple check. If the epoch has changed, then this instruction is to be thrown away. And that's essentially the idea of epochs. And what we will do, either in the next lecture or lecture after that, we're going to actually implement this. Okay, so you have seen now this pipeline, and if you analyze this thing, you will pretty soon discover that this second part is really kind of lengthy part, because you're doing decode as well as you're doing the ALU operation in it. Maybe there is something to be gained by pipelining it further. Let's divide the execute into two parts, decode part and the real execute part. Decode part will go and fetch the registers and pass it on to the next stage. And how do I do that? Right, so we'll have a decode stage and execute stage, and the picture will look something like this. So we have the fetch stage, which passes instructions forward. Until now it was 1 or 2 cycles after that, but now I'm being more aggressive. I'm saying, okay, we're going to split it further, decode stage and execute stage. Why? Because my combinational paths may get smaller and my clock speed may get faster if I do this. That's the reason for finer grained pipelines in general. Now, this is easier said than done. The moment we do this, whole set of new problems arise, right? And these problems, the most important one we have to understand is what is called a data hazard. That how to make sure that the registers that the decode stage reads, it's not reading stale values. That an instruction ahead of me is not going to be writing into R1 if I'm reading R1. Right? So this is the determination that has to be made somehow. The question is how? How do I decide this? One way would be to keep track of it. Say, what are people ahead of me trying to do? Right? And that's precisely the solution we will go after in this case. So we have data hazards. Oh, I see, this is the timing diagram. So this is the code where you have a load instruction trying to load R1, and then in the next instruction I'm trying to use R1. This is a perfect example for how you can end up reading stale values, and let's see how it will work. So I0 comes here, I0 will come here, and you have I1 at that stage. I0 is in the execute stage, but remember it's a load instruction, so it's going to take even longer. And what data is needed by I1? What data is needed by I1? The data that you just got back, right? So if you draw a picture here, so you will see that E1 is execution of E1 can only begin, should begin only after I1 has completed, only after, I0 has completed. And you see this, and the main point here is see the data dependency here. That if you had fetched it something earlier, you just don't have it. You don't have the right thing in it, and therefore you have pushed them aside. This arrow is just a way of saying if there is a possibility somebody is going to be updating that register, be patient, wait. Don't let this instruction move until the instruction that is ahead of you completes. Once it completes, by definition, the value of the register will be correct. Okay, so the question is, how do we do all this? I1 must be stalled until I0 updates the register file, and data hazard disappears. So what I want to describe you next is a mechanism for stalling, mechanism for detecting these things and stalling. And data hazard is guaranteed to be eliminated as the pipeline drains, as the instruction goes towards completion. Okay, this caution is pretty serious. This is a complication, but let's not worry about it right now. We'll have plenty of time when we do the codes for this. All right. What I want to show you is the machinery for doing data hazards. All right. So data hazard arises when the source of this register wants to read R1. How can I be in trouble? Because there is an older instruction that wants to write into R1. So if I keep track of the destinations in which all the instructions ahead of me are going to be writing in, then I have a chance. When I get a source I want to read, I can compare it against that. By the way, is anybody in the pipeline going to write into R1? And if the answer to that question is yes, what do? Stall. Just stall until the answer becomes, now nobody left in the pipeline who will be writing into R1. And that's precisely what we want to record. We want to record that instructions that are ahead of me in the execution stage, what registers they'll be updating. We keep track of all that. Both source and destination registers must be valid for a hazard to exist, because not every instruction has a source and not every instruction has a destination. So you have to pay attention to these details, otherwise you will unnecessarily stall, or sometimes you may not stall because you're comparing against an illegal quantity when there was none to be had. So our current decoder does not record the validity of source fields. We had simplified the decoder for that, but it's a very small modification to the decoder, and I don't remember whether we are expecting you to write it or we give it to them. Brian, what are we doing?
We're giving them a decoder.
Okay, so we'll give you the right decoder, which will mark the sources as, that this is a valid source. So when you compare source and destination, it has to be a valid source and a valid destination. Only then it can be a hazard, otherwise no hazard. All right. Okay, so the data structure we have for this purpose is called a scoreboard. That's where I'm going to keep track of everything. And literally the imagery is like that. You have a blackboard in which you'll keep marking this instruction entered, and it's going to be writing in R1, this instruction entered, and it's going to be writing in R17, etc. And now the next instruction comes, it wants to read R3. You quickly go and consult everybody. Is anybody writing in R3? If nobody is writing in R3, safe, no data hazard. You'll put it in the pipeline. If there is a data hazard, you won't. So initially scoreboard is empty. Compare source of the instruction when it is decoded with the destinations in the scoreboard. Not a very difficult task. Right? Stall the decode from dispatching the instruction to execute if there is a read after write hazard, if there is a data dependency, that is. And when the instruction is dispatched, enter its destination into the scoreboard, because now this instruction is entering the execute phase. So whenever you enter something, there must be a time when you take things out of scoreboard. Otherwise scoreboard will get full. When do we take things out of scoreboard?
After the instruction writes to the register.
Exactly. When the instruction completes, you just say, okay, this instruction is done. Destination corresponding to this instruction should be deleted from the scoreboard. Very good. The install instruction will unstall when the raw hazard disappears. That's guaranteed to happen because pipelines can always drain. They can always empty out. So if you're thinking of scoreboard as a module, right, and that's how you should be thinking about every piece of hardware we design, what are its methods? its methods are going to be, you will search the scoreboard, given a destination, given a source, does it exist? So since an instruction can have up to 2 sources, that's why there are 2 search ports. You can do 2 searches simultaneously, right? And if you're able to dispatch it, then you're going to insert the destination of this instruction into the scoreboard. And when the instruction completes, you remove it. You remove the oldest instruction from the scoreboard. So that's the whole idea behind the scoreboard, and these methods are described here. Let me suggest to you 2 methods for implementing scoreboard. So this is something else you have to get used to in hardware, that when we talk at high level, it seems like a lot of machinery is involved. Oh man, I have to detect the source, and then I have to compare it against all the destinations that are in the scoreboard, and then I have to do something, right? And remember, we are doing this at every clock cycle. So we have to be very, very clever, and we have to pay attention to how much hardware is being kept. This is very different from software, right? You don't say, oh, I can write a program to search it. I'm sorry, that's not going to work, right? You have to design a hardware structure that can search in 1 cycle, that can search immediately what's in the thing. And here are 2 possible answers to that. So one design is just a FIFO, right? So this is a FIFO of the destinations. All the instructions that have destinations, I keep putting them in there, right? So destination, these are register names. And then, what is insert into the FIFO? It's simply an NQ operation. What is remove operation? Simply a DQ. Search is a bit of a problem. What will search do? Search has to give me a source. It has to compare against every entry in the FIFO. So if FIFO was 10 long, right, and you have to compare against 10 things in 1 cycle, that's pretty daunting. Well, 2 pieces of good news. One, how long is your FIFO? How many entries do you need in your FIFO? Anyone? In the scoreboard, how big the FIFO has to be? Anyone? Yep. 2? 3. So remember, fetch stage doesn't play in this, right? Because we are asking this question at the decode stage. So the question is, how many instructions can be ahead of you, right? So if the instructions ahead of you is just 1, your FIFO will be of size. If 2 instructions can be ahead of you, FIFO will be of size 2. So unless you get into designing very sophisticated processor with deep pipelines, right, these FIFOs are not big. You still have to understand its methods, just as you have done with FIFOs, with anything else, right? Because that's the only way you'll get the semantics right. And when you're thinking that, do not think, whether the FIFO has 1 element or 2 elements or 10 elements, right? Get those things right. And then you say, oh, for this problem, FIFO of size 1 will do. For this problem, FIFO of size 2 will do, etc. Nevertheless, let me give you an alternative implementation which is even simpler. And now the implementation is simply, instead of keeping track of the destinations, what I do is I associate a bit with every register. Alright, so if I have register R1 to R32, if somebody is going to be, initially all registers are marked as nobody is interested in writing in them. First instruction comes, it wants to write in R13. I go and flip the bit. I say, oh, this instruction somebody wants to write, so I'll set its bit to 1. That means there is going to be an instruction in the pipeline that modifies R13. Now the next instruction comes. Suppose it also wants to write in R13. What will you do? He says, sorry, I'm busy, go away. Right? Because R13, somebody else is already writing. I can't do all the bookkeeping in this case. There are more sophisticated schemes you can come up with. Besides the point, let's take the easy way out. We just stop. We say, sorry, 13 is already being written. Suppose somebody comes and say he wants to read R12. How do I find out if R12 is being written or not? There are only 32 bits to examine, right? And you're reading one of the bits in that, the 12th one. And if it is set to 1, then you say, oh, somebody's trying to write into this, right? And you will stall. And what will happen when you leave? You'll clear the bit. So this scheme turns out to be very, very simple, counter-based scheme. And lots of people use it, right, as opposed to the first one. And I think I'm told that we are also going to give you an implementation of Scoreboard for your project. Not that it's very hard to implement. All right, now let's try to understand where does this Scoreboard fit in the pipeline? How will we deal with it? So you have seen the other registers. Now I have drawn this Scoreboard also like this. Which are the stages which are interacting with it? In the decode stage, right? After you have decoded the instruction, then you know its sources. So these are the search things. You're asking that question: does this destination, does this source exist in this Scoreboard? And if the answer is no, that means you can insert it, right? So that wire shows insert. And whenever the instruction completes, you'll remove it, right? So that method is the remove method. So this is the interaction that is going on, interaction between various stages using the Scoreboard. You see, another point I'm trying to emphasize here is designing these pipelines is tricky because all the time we are looking at something forward, but we are sometimes also taking action backward. Right? I mean, removing something which people here were reading, but now this guy, which is later in the pipeline, is trying to write it. So there is, whenever you have this, you have possibility of race and many things going wrong in that. If search by decode does not see an instruction in Scoreboard, then the instruction must have updated the state. Oh yeah, this is a very subtle point. I want to think even more abstractly. So when I'm saying search for R12 and you say nobody in the pipeline is writing R12, that was an easy assertion, but there is something more than that is going on. That means anybody who was going to write in R12 is finished doing so. That means the register file has been updated with the value of R12. R12 should not be stale. So if you remove anything from the Scoreboard too soon, before you have updated the register file, hell will break loose. So it's not just a question of checking and removing. There is some high-level invariant you have to maintain, that you can remove an instruction from the Scoreboard only after you have updated the register file. Otherwise, because that's what the assumption is, because I'm going to read it. Right, in this. Okay, thus an instruction is removed from the Scoreboard, it updates the register file, must be visible to the subsequent thing. Actually, it's even more subtle than that, because what you will discover is, this part is easy, that remove and write into the register file must be done simultaneously. Okay, similarly you can say search and reading of the register file must be done simultaneously, because that's instantaneous information. You say nobody is writing into these registers, okay to read it. All right? What is subtle here is, if in this cycle I'm writing into the register file, and in the same cycle I'm reading the register file, what am I going to see from the register file? Does anybody remember, in the same cycle, if I do an update to the register file and I read the register file? Yep.
The read happens before the write.
The read happens before the write, right? That's what, do I have something, you know. So read happens before the write. That's the basic register file we have designed. And here we are saying this read better be visible to the decode stage. And therefore, it has to be a different kind of a register file. It has to be what is called a bypass register file. Much more on that later on. So this is bypassing essentially, as I mentioned to you, this is the normal flow, and bypass will mean that we want to provide an extra path. We want to be able to go directly while we are updating the register file. We want to supply the value to the backstage, and that will be needed in this case for correctness, right? So this is the bypass stuff in this. Bypassing introduces new combinational paths, and sometimes it can make the clock worse. So yes, you will save a cycle, but then now when you do the analysis, you will see, oops, bypass has, you know, my combinational paths in my design have become longer. The effectiveness of bypass is determined by how often it is used. This is just very simple code for register file. All I'm trying to tell you is that what we already discussed, this is the normal register file where reads happen before write. And later on we will see if we can design a register file so that if you write it, that's the value I will get in the same cycle. Writes happen before reads, right? So that's the whole idea behind a bypass. How to design these things will be the topic of the next lecture. So final slide here is, how do I measure the performance of my processor? In very simple terms, all I want to know is how long is my program going to take to execute, right? And if you break it down, you can see how many instructions are there in the program, right? So obviously it should depend on that. And how many cycles every instruction takes, and then what is your cycle time? And these things all have names. So this is called CPI, cycles per instruction. Now from now on, this is going to become part of your jargon. You know, what is your CPI, right? Cycles per instruction. And you will boast about it. Ah, man, I can bring it down, you know, to this and that. Okay. And clock is clock. So to lower, pipelining can lower this thing unless you use too many bypasses. Okay, but CPI has two parts. CPI has this part assuming that everything was perfect in the world, which is we call ideal CPI. You will never achieve that, never, right, in any realistic program. So why don't we achieve that perfect situation? There are many, many reasons why you're going to lose, right? Because you're going to lose because you have long latency operation. You're going to lose because your prediction was wrong. You're going to lose because you encountered a data hazard, right? So what I have done is I have set up two boundaries for you. On one hand, we know what the ideal is. Ideally, we can execute an instruction every cycle. But we are not going to achieve that ideal because there are many, many reasons, you know, why we have to introduce bubbles in the pipeline. And the whole exercise is about how to reduce these number of bubbles without making combinational paths too long, otherwise the clock itself will get slower. We'll continue with this topic in the next lecture, which will be much more focused on implementation. Thank you.